Today we'll be looking into the summation of a sequence, and in the previous video we looked at sequences with a common difference of 1. But now I'd like to go to different sequences where the common difference is not 1, so that we can look at more diverse group of sequences. So let's just go ahead and start off with a sequence of 1 plus 4 plus 7 plus 10 plus 13 plus 16. So in this sequence, we have a common difference of 3 between each of the terms. And I just want to point out that we'll be dealing with arithmetic sequences. So I want to make that clarification. In an arithmetic sequence, we only add to the previous term. We don't do any other operation. Well, we may subtract, but that's the same as adding a negative number. But we won't do any operations like multiplication on the previous number. Those will lead to completely different formulas, which I may go over in the future. So for now, we'll be dealing with sequences where we consistently add some number to each previous term. So in this case, again, the common difference is 3. And the reason why the previous formula doesn't work is because the last term, the nth term, is no longer n. So let me give you an example just to make it clear. So in the last video, let's say we had a sequence like 1 plus 2 plus 3 plus 4 plus 5. The nth term, or the fifth term in this case, was also the number 5. So the nth term was n, which is very key for that formula, for the formula n times n plus 1 over 2. It's very key that this nth term will be n, so that this n plus 1 will make sense. Because this n plus 1 is in reality just this 1 plus 5, as we observed. So this is very key to this idea. And this is the reason why these sequences are different. We end with a 16 over here instead of a 6. There are 6 terms in the sequence, so before we would have ended with a 6, but now we end with a 16. So that's the key difference that I want to start off with in this video. So how will we approach this? Well, we will approach it in a similar manner that we did with the common difference of 1. We want all of these to become some sort of common number that we can just multiply out by the number of terms. So similarly, we can just add the duplicate of the sequence in reverse, and we'll get 16 plus 13 plus 10 plus, we have 7 plus 4 plus 1. And so notice how we're just adding the same sequence in reverse. And this is one of the most creative ideas when trying to think of a formula, finding out how to manipulate the original expression in a way that makes it easier to simplify the resulting expression. So when we add all of this together, we'll get 17 plus 17 plus 17, and this makes it much easier for us to multiply out with this number. So you'll notice that what we get is simply 17 times 6, because there are 6 17s. Now why is there 6 17s? Well, it's because the original sequence had 6 terms in it, and notice that there's a 1-to-1 correspondence with the number of terms in the original sequence and the number of terms in our final output. There is no carry forwarding or anything, because we're adding each of these terms separately, so there won't be any added terms or subtracted terms. So in this case, we'll just have 17 times 6 And remember that since we duplicated the original sequence in here, we have to divide by 2 to cancel out that duplication. So now we have 17 times 6 over 2, which is also 17 times 3, which is 51, because you can do 17 times 3, which is 10 times 3, so that's 30, plus 7 times 3, which is 21. So that becomes 51. And now that we have this formula over here, let's see if we can generalize it. Let's see if we can figure out a way to apply this to any sequence given a common difference of some number, the first term, the last term. So we want to see what exactly happens over here. So let me go back. So we want to observe what actually happened during this process. So what are we doing here? We'll notice that 1 plus 16, just 1 plus 16, is 17. So the number that we were multiplying with the number of terms in the sequence was 17, which we originally got by adding the first term and the last term. And that's one of the key parts to this sequence. So we'll start building our formula over here. So we have the number of terms multiplied by the first term of the sequence plus the last term of the sequence. So we'll usually denote this as a with a subscript of 1, which is the first term, plus a with the subscript of n, which is the nth term. So we'll have n times the first term plus the last term. Now, why does this hold all the time? Let's just pause and get an intuition of why this holds. So what's actually happening here is when you're adding 3 over here in the first sequence, in the sequence that is on top of this sequence, we're adding 3. We're also subtracting 3 in the second sequence. So why does this work? Why do they cancel out? Well, if you imagine what's happening here, the second term plus second to last term, which is 4 plus 13, will actually just be 1 plus 3, which is the first term plus 3, plus 16 minus 3. So this is 4 plus 13. Notice that the 3 and 3 cancel out, and we're just left with 1 plus 16, which is 17, which is also the first term plus the last term. So that's why this holds all the way through. It's linearly increasing from this side and linearly decreasing from this side at the same rate. So this is very important. So finally, we also want to have our all over 2 here, because remember, we have to cancel out the duplicate of the sum over here. Now I want to pause and notice that we didn't actually use the common difference over here, which is probably the most interesting part about these formulas. So you have the number of terms and the first term and the last term, but we never use the common difference. Now, you can pause and think about why this is, but I'll go over it. So basically, the common difference is actually related to these 3 variables. So for example, if you have all 3 of these, then there's only one possible common difference you can get. Now think about why this is. Since we're going at a constant rate on each of these sides, each of these steps, there will be a total of 5 steps, or in a more general case, n minus 1. So since we didn't actually explicitly state the common difference over here, how can we derive it from just this? It may be obvious, just like, okay, well, it's increasing by 3, so the common difference is 3. But let's say with this general formula, it's kind of more difficult to see where the common difference would come from. So you can think about the common difference as the total distance moved from 1 to 16 divided by the number of steps. So we have 5 steps, so that'll be in our denominator over here. And notice that we moved a total distance of 15. So that means our hops were of size 3, and these hops is just a very simple way of saying the common difference. So our common difference was 3. So we don't actually need the common difference in order for this formula to work, because these 3 variables imply the common difference. They work together cohesively. So now that we have seen this, let's also look at a more general sequence. Something that is, we want to show how to derive this formula without just using numbers. We want to use some more general terms so that we can prove that it works for all other real numbers. So let's look at that over here. So we'll start with a, and usually we had referred that to as a sub 1, but we'll look at it as a here just to make it easier to write. And we'll let the common difference be the variable d for difference. So now, when we sum these, we have the first term plus. And notice that the second term will just be the first term plus the common difference, which is 3 in this case, but we have renamed it to d in this case. So a plus d, and notice that when we continue, we have a plus d, which is a plus 2d. So remember, all we're doing is adding the common difference to each of these terms. And this will go on until a plus, wait a minute, how many terms are in this sequence, and what do we actually multiply to d over here? So we have to figure out, wait, what is the coefficient? Here we had 0, here we had 1, here we had 2. So if we went from 0, 1, 2 here, if we go to n here, will that actually equal n? Let's see. Let's say we had 5 terms. Let's say we had 5 terms in the sequence. We know that we have a 0 coefficient of d here. So just to make that clear, I want to write there's an invisible plus 0 times d over here. Just to make it clear that we're going from 0d to 1d, and then so on. So let's say we had some generic sequence of starts from 0 to 1 to 2, 3, and so on. And let's just keep going and stop at 5. So in this case, n is actually 6. Notice there's 6 numbers in here, even though our last number is 5. And this is a key point in here. Notice that there's 6 numbers, but the last term in this basic sequence is 5. So we actually have n minus 1. So that's why we have a coefficient of n minus 1 times d at the very end. N minus 1 times d at the very end. And pause this video, just try to truly understand that, because it's very key to noticing how we stop at n minus 1 instead of stopping at n times d. So now that we have this, we can just continue with using an application of this formula. So we'll do it the same way. So the first term is a plus the last term, which is, or I'll also do this in the correct color. So we have the first term, which is a, as we saw over here. We have the last term, which is, as we have figured out, a plus n minus 1 times d. and then we'll multiply all of this times n. And again, we also have to do our division by 2. So we can also simplify this. To 2a, because these two a's will combine, plus n minus 1 times d multiplied by the number of terms, which is still n. And finally, we'll have this all over 2. And this is very neat, because here we didn't know the common difference. And here we weren't given the last term. But in both cases, we didn't need either of them given to us because they correlate with each other. We saw that this formula is just an application of this formula. So once you notice the relation between these two formulas, it's very nice to see how you don't always need one of the variables. And I'd like to see if you can also figure out, let's see, can I make more formulas without others of these variables? And like for example, if I had 3 different variables, do I need the 4th one? So I want to see if that's possible. So try that out. And so I hope you found this interesting, because now we know how to sum a sequence that has a common difference other than 1. So that it's a more diverse class of sequences. And we have also shown how to show that for a general first value a and a general common difference t, and a general number of terms n. So I hope you found that interesting, and thank you.